So in problem number 3, I have a tennis ball in the picture, goes from rest. At the end of the hill, it becomes airborne at an angle with respect to the ground. Determine the range or change in x. Okay. So this one kind of breaks down to multiple pieces. I can see here I have changes in height. So to me, anytime I have a change in height, that is screaming energy, solve it that way. Here, range, that's a projectile flying through the air, so I have to do two things. Could I just do the range piece? Well, you have an object at an unknown velocity at 35 degrees. Right? Comes back and lands on the ground. So I know that the change in y is 0. I know the acceleration is negative 10 meters per second squared if I made down negative. But after that, I don't really know anything. So what do I do? Well, if I solve that velocity, I can do it. So I can compare this point and this point when I'm doing energy, when you have changes in height. So let's do that. Energy at the top plus work non-conservative equals energy at the bottom. So energy at the top, that is potential energy, which was mgh. Wasn't moving, so no kinetic energy. Wasn't rotating, no rotational kinetic energy. The only forces acting here are gravity. Gravity doesn't do work non-conservative. Normal force does 0 work. We do have friction to roll, but we also know rolling friction does conservative work, not non-conservative work. So then that is not there. After that, we know at the bottom of the hill, or at the bottom, not at this, at the bottom, you have kinetic energy and rotational energy. Let's look at this one. Now, if you made this height equals 0, you would also have potential. But we can simplify that, and all we have to do is worry about this height. That's height equals 0, so at this location, right before it's launched, it has 0 potential energy. So this is my equation. Just like we've done before, let's continue to do it again. Convert everything to linear. This is going to be 1/2, 2/3, mr squared, v over r squared. Hopefully this is getting repetitive. Those cancel out, so I'm left with mgh equals 1/2 mv squared plus, that's going to be 26 mv squared. So 1/2 mv squared plus 26. Well, masses cancel. Lowest common denominator is going to be 6, so that's 3. So I have 5, 6 v squared equals gh. So velocity equals 6 gh over 5 and square rooted that. Then plug in your numbers. I know g is 10 and I know h is 1.8. Plug in those numbers and I get a velocity of 4.65 meters per second. Now, all of that was done just to find this hypotenuse velocity. So this velocity was 4.65 meters per second. And this is a great one to practice some of your kinematics. Now I could find Vx and Vy. My Vy, and I can do my Vx using trig. So let me pause this. You can do the same, and let's list all the other variables we may know. Here's the variables that I ended up with. V initial in the y is 2.67. V initial in the x is 3.81. Now I can see this is a perfect parabola, so the numbers over here and here are the same, except one is up, one is down. So the final is negative 2.67. We know Vx doesn't change because there's no forces in the x. So now how do I find that distance? Well, we know range is change in x equals Vx times t. And we know this is 3.81, but I don't know t. So I find t in the y variables. We have every y variable listed, So let's use the simplest equation. Okay. Plug in your variables and see what you get. Okay. I ended up with 0.534 seconds. So 0.534 seconds here. And I get a change in x of 2.03 meters. Right, so that one was tying a lot of concepts in, but now you're seeing the pattern of rotational energy. Let's see, 2.03 for question number 3, so that's great.